So continuing with this third video in the lecture series, this is the second video by Professor Lewin, and yeah, let's get on with the show.
Today I'm going to work with you on a new concept, and that is the concept of what we call electric field. We spent the whole lecture on electric fields.
Alright, so I would contend there's no such thing as an electric field. There's just the phenomenon, two phenomenons. One is the pressurization of an atom, and the fact that you can convey that pressure through atoms. That's what we know is electricity moving through conductors, and that's, you could call electricity. Electricity is pressure moving from one atom to another atom to another atom. Magnetism is another phenomenon. They cause each other. The force of magnetism is the force that compresses the atoms or decompresses them, and so it creates electricity in a sense, but it's the only thing that has a field. So the only field created is a field of the effects of the fact that the electron and the proton are in fact monopoles of magnetism. Sorry, my computer monitor is not behaving. Very distracting when it does that. So let me just pop this image up and just for a little bit of a highlight. So the electron and the proton exist as two distinct polarizations or type of matter, and there are two types of force that are complementary to those types, red and black. And as stated in previous videos, the forces, the common force would reflect, so red force would reflect off a proton, and black force will exit perpendicularly, and the inverse would be true for the electron. This allows there to be the creation of a great deal of pressure between electrons and between protons and protons, because the reflections would mean that any force would continue to rebound. And the idea would be is that when the objects are further apart, the force is relaxed and that there's less impacts and less pressure. When they're close together, there's more impacts, more pressure. Now, when protons and electrons are next to each other and in contact in some way, the truth is all the forces that we're reflecting will not exist anymore. There won't be any reflections between them, because all the black force will leave perpendicularly from the red object, and all the red force will leave perpendicularly from the black object, and you can't create any reflections, permanent reflections. Therefore, you have very low pressure, and the two objects move towards each other. And when you have a bunch of these things in arrangement, what will happen is there'll be a subtle differential. There'll be red force will tend to channel in one direction, and black force will tend to channel in the opposite direction. So each one will do that by a little fraction of an amount, and if you add a bunch of them together, the amount of differential becomes bigger and bigger, and you end up with a substantial force that we call magnetism. So, but this is what charge is. Charge is the electron and the proton. It's their nature. It's their fundamental property. We call that charge, and that is not electricity. Electricity, again, has to do with the electrons being under pressure, having that force in them. And obviously, in a circumstance where the force can be drained, that's going to create a change in pressure, and so you can change the pressure of the electrons, and that's the electrical effect. But the electrical effect is a consequence of the fundamental property of charge, and charge is substantially what creates magnetism. So it's a magnetic feature more than it's an electrical feature. A lot more magnetic than electric. And so in this video he's going to be describing the electrical field. It's not going to be the electric field, it's the magnetic field. I think that's enough. Yeah, sorry, this it's a broken button, so the monitor keeps auto-configuring when nothing needs to be configured. So it just keeps popping this annoying screen on the monitor, and it's really distracting. So, well, I'll have to learn to live with it, I guess.
If I have a charge, I just choose Q, capital Q and a plus at a particular location, and at another location I have another charge, little q. I think of that as my test charge. And there's a separation between the two, which is R.
Alright, this always comes up in gravity. It's the same kind of problem. The only way you can really measure something is you have to put something in the field to measure it. Just like you can't measure gravity unless you put something to get measured. So when he says a test charge, he's saying, I'm using this to test how strong the gravity is. So he's not really considering this thing's effect on the Earth. He's just really considering the Earth's effect on this thing. Sort of.
The unit vector from capital Q to little q is this vector. And so now I know that the...
Alright, so by the vector he means the strength of the differential in what I drew as colored arrows. So you could argue that the charges by their nature are going to create a change in the environment, and the vector is really just a description of how much change it's capable of creating. So its weight as a charge.
Two charges, if they were positive, let's suppose that little q is positive, they would repel each other. Little q is negative, they would attract each other. And let this force be F. And last time we introduced Coulomb's law. That force equals little q times capital Q times Coulomb's constant divided by r squared in the direction of r roof. The two have the same sign. It's in this direction. If they have opposite sign, it's in the other direction.
Yeah, so that just kind of confuses things. And, well, I mean, using a capital Q and a Q and not establishing that there's fundamental differences between them. So in the sense that one's positive and one's negative, one's positive, or just as positive. Yeah, it fundamentally changes the relationship. So two electrons meeting each other, very different than electron and proton. So electron and proton, all the force leaks out, no pressure. Electron and electron, none of the force, the black force leaks out, therefore more pressure. And the closer they get, the stronger the pressure gets.
And now I introduce the idea of electric field, for which we write the symbol capital E. And capital E, at that location P, where I have my test charge little q, at that location P, is simply the force that a test charge experience divided by that test charge. So I eliminate the test charge. So I get something that looks quite similar, but it doesn't have the little q in it anymore. And it is also a vector. And by convention, we choose the force such that if this is a positive test charge...
So they just arbitrarily establish plus and minus again. But regardless, this stuff you really don't need to understand too much, except understanding the vector lines are basically going to represent a direction and an intensity. So the longer the line, the more strength it has, and then the direction will be in what direction this bias exists. And essentially he's going to validate what I said in the previous video about the fact that you're just going to sit there and add these vectors and come up with a net vector. So you're just going to add the arrows and they'll add up to a net effect if you have more than one body affecting the circumstance.
Then we say the E field is away from Q if Q is positive. If Q is negative, the force is in the other direction, and therefore E is in the other direction. So we adopt the convention that the E field is always in the direction that the force is on a positive test charge. what you have gained now is that you have taken out the little q. In other words, the force here depends on little q. The electric field does not. So the electric field is a representation for what happens around the charge plus q. This could be a very complicated charge configuration, and electric field tells you something about that charge configuration. The unit for electric field, you can see, is newtons divided by Coulomb in SI units. And normally we won't even indicate the unit. We just leave that as it is.
Yeah, because, yeah, so no one pays attention to trying to understand exactly how strong any of this stuff is, because it's in some bizarre quality of a Newton over a Coulomb, like somebody knows what that is.
Now, we have graphical representations for the electric field. Electric field is a vector, so you expect arrows. And I have here an example of a charge plus 3. So by convention, the arrows are pointing away from the charge in the same direction that a positive test charge would experience the force. And you notice that very close to the charge, the arrows are larger than farther away. That sort of is trying to represent the inverse R² relationship.
So the inverse square law that applies just like gravity. So the same kind of drawing could be made for gravity with the arrows going the opposite direction. But the real point is that it's just about how much force, either absorbing it, understanding is how much force you would have to absorb to move something versus how much if you reverse the circumstance and you became a light bulb. So it's like thinking about it like how much light it would take to move your mass versus thinking about how much light you would produce if you produced light. It's proportional to this element of density of this charge. So when he says plus 3, it's just saying this object has a density of ability to affect the field that would be 3 times something that has a 1. Or plus 1. Well, minus 1 is really, it's the two charges are different, electron, proton. So plus in this case means something versus minus. In the case of electricity, it doesn't mean much, but in this case it does mean something in the sense that these are opposite charges. So one's electron and one's proton. One's affecting one field of gravity and the other's affecting the other field of gravity, in the sense of the forces have 2 elements and the matter has 2 elements, 2 charged elements. But again, this is just what a magnet would do and just what gravity would do. There's no electric field. This is just describing the magnetic field around electrons and protons.
Of course, it cannot be very quantitative. But the basic idea is, this is of course spherically symmetric if this is a point charge. The basic idea is here you see the field vectors and the...
See, if you could take a magnet and break it in half and it didn't actually turn into a new magnet, that is, create 2 new poles, and, you know, if you could actually take all the protons from the atom, from the magnet, all the protons, and move them to one end, and all the electrons and move them to one end, you'd have a kind of monopole. So he's describing magnetism using monopoles. And it's exactly what electrons and protons are. They're essentially magnetic monopoles. And if you broke magnets, if you could break them, this is how they'd behave. If you could break the north end off and keep a north end over here and a south end over here, he's describing here that phenomenon, monopoles.
Direction of the arrow tells you in which direction the force would be if it is a positive test charge, and the length of the vector gives you an idea of the magnitude. And here I have another charge -1. Doesn't matter whether it is -1 Coulomb or minus micro Coulomb, just it's a relative representation. And you see now that the E field vectors are reversed in direction, they're pointing towards.
So these are arbitrary. There's no vectors pointing, moving in a direction, in the sense that where he's drawing arrows going in, okay, that means it's a negative charge. That means it's an electron, let's say, or a proton. And when he draws the arrows going out, it's an electron. So he's using in and out arrows to analogize as a metaphor for electron energy versus proton energy, the red versus the black force.
The minus charge by convention, and when you go further out, they are smaller. And you have to go all the way to infinity, of course, for the field to become zero.
Now, what he should have done with that drawing, it's too bad it's not still there, is to, with the charge that's bigger, to make more lines, 3 times as many lines, and then to make as a one charge. And then you'd get an idea that at a distance, the separation between the lines on the 3 charge is still pretty close, where on the 1 charge they've gotten much bigger. So we're sort of back to this argument that it's perspective when it comes to charge. And once you have them the same size, okay, you've taken things that are different size and you made them same size. Now if you move this whole thing backward and forward, that size difference will always be essentially the same. And so now it just behaves as if it was to these size things from a distance. Sorry, monitor trouble still. Oh, I don't know why it's. I guess I have to tear out another button.
Because the 1 over r square field falls off, and you have to be infinitely far away for you to not experience, at least in principle, any effect from the charge. What do we do now when we have more than one charge? Well, if we have several charges, here we have Q1, and here we have Q2, and here we have Q3, and let's say here we have Q of I, we have I charges. And now we want to know what is the electric field at point P. So it's independent of...
I don't know why it does the QI thing, implying some other higher numbers or something. I mean, you know, you do have to quantify what ones you're including. You can't have just Q any amount possible and actually do a useful equation.
Of the test charge that I put here. You can think of it, if you want to, as the force per unit charge. You've divided out the charge. So now, I can say, what is the E field due to Q1 alone? Well, that would be, if Q1 were positive, then this might be a representation for E1.
Alright, so they're just going to be vectors. And the point would be is to draw the arrows to identify what the magnitude of Q1 at P. So the line he would draw would just be a line pointing out that from that at that distance there's this much effect, just like from gravity. The further away you go, the weaker the gravity gets, so the shorter the line you would draw. So right on the surface you'd have a big line, higher up you'd have a much shorter line. And then the point will be just to add this line, and let's say we had the moon was the other thing we were considering, and that had a line going this way, so the Earth line was twice as long as this line. Well, then you could say, well, the average between these two lines would be this line, but since the Earth is twice as strong, it goes here instead. So you have to add the magnitude and the direction. So if they were the same magnitude, you just say the average between the two is this way. So that would be the product of your mathematics. So you just start adding. So you just add 2, you get this, and if there's another vector going this way, then you just add those 2 and you get this, and then you add another vector going this way, then you add those 2 and get this. But you have to consider the magnitude too.
If Q2 were negative, this might be a representation for E2, pointing towards the negative charge. And if this one were negative, then I would have here a contribution E3, and so on.
And so all you would do is start averaging these. Okay, so the ones that were, again, presuming they were all of equal magnitude, it would be really easy. You just average this one, come up with this line, then you average these 2, and you come up with this line, and now you're done. When they're different magnitudes, then you have to consider that the magnitude is going to bias it in the direction of the bigger arrow, and so there's going to be the line won't be an average of the 2 arrows, it'll be an average plus the magnitude.
Now we use the superposition principle, as we did last time with Coulomb's law, that the net electric field at point P it's a vector, is E1, influence of charge Q1 plus the vector E2 plus E3, and so on.
And adding vectors is doing exactly what I just said, which is basically just averaging. So you just take the two vectors and you come up with the average. So it's just what I was saying.
If you have I charges, it is the sum over all I charges of the individual E vectors. Is it obvious that the superposition principle works? No. Does it work? Yes.
I don't even know why he says that. It seems quite obvious that, yes, this adding vectors makes perfectly good sense. Sure, it should work. Yeah, it makes sense to me. So I don't know why that is a cognitive issue for somebody else. It seems exactly how you would do it. If I'm in the wind and there's a fan blowing me one way and the ocean's blowing me another way, I know the way I'm going to get blown is going to be based on how strong this direction is and how strong this direction is, and I'm going to go something like this. Completely intuitive.
How do we know it works? Because it's consistent with all our experimental results. So we take the superposition principle for granted, and that is acceptable, but it's not obvious.
Again, it is obvious. You just add the forces. That's superposition. Add the forces. Don't think about how the forces are mixing. Just add their effects. Rock came this way. Rock hit me from behind. I don't consider anything about the two rocks. I don't mix them in any way in terms of trying to blend the rock throwing. I just say I have an effect in this direction and I have an effect in this direction, and I add them. No big deal.
If you tell me what the electric field at this point is, which is the vectorial sum of the individual E field vectors, then I can always tell you what the force will be if I bring a charge at that location. I take any charge that I always will carry in my pocket, I take it out of my pocket, and I put it at that location. And the charge that I have in my pocket is little q. Then the force on that charge is always q times E. Doesn't matter whether q is positive, then it will be in the same direction as E. If it is negative, it will be in the opposite direction as E.
So it doesn't make much sense, but he's just basically saying that if you just change the polarity of P, you'll reverse what you just said. But so what?
If Q is large, the force will be large. If Q is small, the force will be small. So once you know the E field, which could be the result of very complicated charge configurations.
All right, so again, he keeps calling it an E field. There's no E field. It's just about what monopoles, magnetic monopoles, how they will behave.
The real secret behind the concept of an E field is that you bring any charge at that location and you know what force acts at that point on that charge.
He's just saying I can, if there's rocks coming this way and there's rock coming from behind me, I can just remove me and put anything here and it's going to be hit by those rocks. I mean, yeah, okay. Unremarkable.
If we try to be a little bit more quantitative, suppose I had here a charge plus 3. And here I had a charge minus 1. Here's minus 1. And I want to know what the field configuration is as a result of these two charges. So you can go to any particular point. You get an E vector which is going away from the plus 3. You get one that goes to minus 1, and you have to vectorially add the two. If you're very close to minus 1, it's very clear because of the inverse R-square relationship that the minus 1 is probably going to win. Let's, in our mind, take a plus test charge now.
So this is just this argument again. I mean, obviously, if you have two things that are, positive and a negative, it doesn't really matter how strong this positive is, like the sun and the earth. We're on the earth. We're going to be affected much more by the earth because the inverse square law has made the sun really weak. And the earth is we're really close, so the inverse square law hasn't destroyed its gravity. So primarily we're going to be occupied by the earth's gravity, and the sun's gravity is going to be kind of irrelevant, even though the sun is gigantic. But you go a distance away, the planet Earth becomes irrelevant, and the only thing Saturn is seeing is the sun. It couldn't care less about the Earth. So the inverse square law has revealed the smallness of the Earth, and it's revealed the largeness of the sun. So, and the Earth has just become nothing, almost.
And we put a plus test charge very close to -1. Say we put it here. Even though +3 is trying to push it out, clearly -1 is most likely to win. And so there will probably be a force on my test charge in this direction. The net result of the effects of the two. Suppose I take the same positive test charge and I put it here, very far away, much farther away than this separation. What do you think now is the direction of the force on my plus charge? Very far away. Excuse me? Why do you think it's to the left? Do you think -1 wins? So we really think the -1 is stronger than the +3 because the +3 we push it out and the -1 tries to lure it in, right? If the test charge is positive. Imagine you all the way to Mass Avenue.
I sort of don't much like this teaching technique of asking a question and finding somebody who's going to answer the question wrong and just kind of humiliating them. I don't know if that does much for people's cognitive interaction. I just don't think it's a whatever, short quizzes, spontaneous quizzes, I don't think is a way to enhance absorption of information.
You think that this distance matters?
See, his drawing, he should have made it clear that this little dot he drew isn't there. It's a mile away. So, you know, from a mile away, the difference between the 3 and 1 distance by the inverse square law is going to mean nothing. Absolutely nothing. And so, yes, the net is going to be the +2. The Earth becomes irrelevant. From a distance, if the +3 was the sun and the 1 is the Earth, you could just understand from a distance the Earth is nothing.
Who thinks the force is in this direction? Who thinks it's in this direction? Very good. You've helped them, really. The force is obviously in that direction because if you're very far away, the field will be the same as if you just had a +3 and a -1 somewhere here, which is +2. So if you're far away from a configuration like this, even if you're here, or if you're there, or if you're way there, clearly the field is like a +2 charge and falls off as 1/r². So therefore, if you're far away, the force is in this direction. And now look, what is very interesting. Here, if you're close to the -1, the force is in this direction. Here, when you're very far away, maybe I should be all the way here, it's in that direction. So that means I must...
So this is the same as my pressure argument, that merely by moving the electron in and out, all right, you change it from a positive ion to a negative ion from a distance, from a perspective outside the charge. So from the outside, there's a there's a point where it's neutral, where they both end up being the same size as pointed out, and outside that point this looks big, and inside that point plus minus. It changes the magnetism of the atom. Stated simply, it goes from being a north pole monopole to being a south pole monopole.
Be somewhere here a point where the E field is 0. Because if the force is here in this direction, it ultimately turns over in that direction, there must be somewhere a point where E is 0, and that is part of your assignment. I want you to find that point for a particular charge configuration. So let's now go to some graphical representations of a situation which is actually +3, -1. Try to improve on the light situation. And let's see how these electric vectors, how they show up in the vicinity of the...
So these are just monopole vectors. They're not electric, they're magnetic, and they're being described as if you could create something called a monopole. If you could create... See, all these diagrams are a reflection of the function of the electron and the proton, essentially. And well, and objects that have charge on them, because that charge is monopolic. So when you charge a balloon, you don't create a red and black magnet. You're just creating the black end, And if I create something that's negatively charged, I'm creating the red end. I'm creating monopoles of charge. So you have to just understand the distinction. This is magnetism described as monopoles, not as a dipole, not as a regular compass needle style magnet. It's the compass needle cut in half, and you can test just the north force or just the south force.
These two charges. So here you see the +3 and the -1, relative units. And let's take a look at this in some detail. First of all, the length of the arrows again indicates the strength. It gives you a feeling for the strength.
It's not a very good illustration. It's not any better than mine, in the sense that it's not very symmetrical. But like I said, it would probably be best to illustrate it by having the dark lines, the thick lines for the 3 charge, and then use like a small pen for the other charge to recognize that it's a much weaker arrows, you know. So you don't necessarily get much of a feel for that.
It's not very quantitative, of course. And so let's first look at the +3, which is very powerful. You see that these arrows all go away from the +3, and when you're closer to the +3, they are stronger, which is a representation of the inverse R² field. If you're very close to the -1, the arrows are pointing in towards the -1, because the 1 over R², -1 wins. And so you see they're clearly going into the direction of the -1. Well, if you're in between the plus and the minus on this line, always the E field will be pointing from the plus to the minus, because the plus is pushing out and the minus is sucking in, so the two support each other.
All right, a point that needs to be raised is when you're doing this with objects that are magnetic because they're made of a bunch of atoms, so like the balloon argument. When you bring these charges near each other, what happens is they could have been, their little magnets could have been pointing in all directions, you know, north-south, to create this idea of north pointing all the way out, or however you want to look at it. And what's going to happen is now they're going to all bend towards that charge. So they're going to be affected by the charge, and they're going to, the elements are going to have a higher density in the direction they're being attracted to. So now they're not going to be able to radiate force forever in some directions. You know, that radiation is going to be essentially not the radiation, but the orientation of them is going to be altered in such a way as they won't really radiate the force out this way anymore, because this has turned all of the monopoles in a direction. The density of the force is going to be coming out towards the thing that has affected it, that it's attracted to. And if it's repulsion, exactly the opposite will happen. All of it will go out that way instead of going this way, towards. So it makes it a little bit complicated, but not much. You can sort of understand the things are affecting each other more than just the force hitting them. The force is creating an incentive, say it that way, for them to turn. And they do.
But now if you go very far away from this charge configuration, anywhere, but very far away, much farther than the distance between the two charges, so somewhere here, or somewhere there, or somewhere there, or here, notice that always the arrows are pointing away. The reason is that +3 and -1 is as good as a +2 if you're very, very far away. But of course, when you're very close in, then the field configuration can be very, very complicated. But you see very clearly that these arrows are all pointing outwards.
Yeah, well, that's just because of his illustration. The really point is that there would be a mixture, but you're always going to have, the mixture is always going to be 3 to 1, or 2 is a net. So you'll get hit by 1 black arrow, right? And for every 1 black, you're going to get hit by 3 reds. So it's the color, if you mix that, is still going to be decidedly red, but it's not it's not technically red. is a mixture. You will get hit by the other color. So this drawing isn't really fair to the truth.
None of them come back to the -1. None of them point to the -1 direction. And that's because the +3 is more powerful, and then there is here this point, and only one point whereby the electric field is 0. If you put a positive test charge here, the minus will attract it, the plus will repel it.
Yeah, well, that's the whole point. The minus can't attract it and the plus can't repel it if nothing's hitting it but red force, repulsive force. That would end up meaning all it does is move out. So clearly what it's doing in that neutral place is it's doing this. All right, it does get hit by the other force. It just moves back and forth. It gets hit by exactly as many blacks as it gets hit by reds. So if the reds moved it in and the blacks moved it out, it's just going like this. So it's in one spot. It's not leaving this area, but it's not being affected. It's not in a truly neutral place. It's in a place where you get yin and then you get yanged in equal proportions.
And therefore there comes a point where the two cancel each other exactly. Now there is another way of electric field representation which is more organized.
I just say it again.
And we call these field lines. So you see again the +3.
This is not electric. This is magnetic. Say it again. Monopoles.
And you see there the -1.
So if you could break a magnet and put a small piece of the North Pole there and a big piece of the South Pole there, or is this red and red? No, they're moving towards each other. So that's not repulsive. Yeah. I can't see very well.
If I release right here, or I place here, a positive test charge, all I know is that the force will be tangential to the field lines. That is the meaning of these lines.
I think that's saying it the wrong way, tangential. It'll be in the exact vector at exactly that point. So it'll be exactly in the direction at that exact point. See, the arrow is changing as the line curves. The arrow is changing. It will be exactly where the arrow is moving at that exact point. It won't bend with the arrow. It'll go straight.
So if I'm here, the force will be in this direction. If I put a positive test charge here, the force will be in this direction. And of course, if it's a negative...
See, I think it's better to draw these in the topographical ways. He has the arrows in sort of a topographical location, you know, the same, equally distant. But if you draw it that way, you can sort of understand that the force will always be parallel to the circle. So if you draw it as a continuous line in radials around, then you can draw that little force line really easily because it'll be completely perpendicular to the surface, the curve of the surface.
Negative charge, the force flips over. So the meaning of the field lines are that it always tells you in which direction a charge experiences a force. A force.
It's just telling you that the one little bit is throwing small rocks at you, the big bit is throwing big rocks at you, and depending on the kind of rock, okay, it's a rock that makes you move the opposite direction. So it's some kind of sticky rock, you know, frog tongue. You're getting hit by either frog tongues that are pulling you, or you're getting hit by rocks. And at every location, there's a certain amount of frog tongue and a certain amount of rock.
A positive charge always in the direction of the arrows, tangentially to the field lines, and a negative charge in the opposite direction. How many field lines are there in space? Well, of course, there are an infinite number. Just like these little arrows that we had before, we only sprinkled in a few. But of course, in every single point, there is an electric field, and so you can put in an infinite number of field lines, and that would make this representation, of course, useless.
So yes, but it would be good to put in a proportional number. So an infinite number, yes, would be. So that's why I've said before that these lines are arbitrary. They're not. They're for illustration. They're not about a reality. There are no field lines in reality. There's just force in reality. An amount of rocks are hitting you, an amount of frog tongue is hitting you, and that's all there is. There's no lines of anything. But to represent it, you're just trying to represent the proportions. Alright, let's see, this hasn't frozen. I was just a little concerned that something might have glitched. So we appear to be okay. And so when he says you don't want to draw an infinite number, but what you do is if you draw a proportional number, that is if the charge is big, you draw a bigger number of lines, and that will give you a better illustration of how strong the force is. By drawing the same number of lines, you lose the fact that there's a proportional separation of the lines that's proportional to the strength of the field at a location. So the further away the lines are, the weaker the force is. So if you draw more lines for the stronger charge, then you'll get the idea that they stay close together at a further distance.
Always limit ourselves to a certain number. If you look very close to the -1, notice that all the field lines come in on the -1. We understand that, of course, because the field lines want to go to the -1. If you're very close to the plus, then...
So that's just the catch, that if you're close to the Earth, and far from the sun, you'll fall to the Earth. But it doesn't change the fact that if I do go out somewhere else, the Earth's gravity is still affecting me. It's only I'm getting very little frog tongue from the Earth, and I'm getting a lot more from the sun at a distance. So it just changes the proportion of the effect. It doesn't change the fact that so there's, in a sense, this diagram is deceptive, because it's implying that the little charge has no effect at a distance. It has an effect. It's just proportionally very small.
And they all go away from the plus, because they're being repelled. You can sort of think as these field lines, if you want to imagine the configuration, that the plus charges blow out air, like a hairdryer, and that the minus suck in air, like a vacuum cleaner.
So it's sort of another, I think, a bad analogy, because they are both charges are doing the same thing. They're just doing the opposite. So, in terms of reflecting their own type of energy, blowing, and bending the opposite version. So if you want to use those two, sucking and blowing, they're both sucking and blowing. They're just sucking and blowing opposite things. So that's the key difference. They can both be blowing, but what they're blowing is opposite force. So it's automatically, the other guy's blowing looks like sucking to you, and when you're blowing, it looks like sucking to him, if you're opposite charges.
And then you get a feeling for, there is on the left side here this hairdryer which wants to blow out stuff, and then there is that little sucker that wants to suck something in, and it succeeds to some degree. It's not as powerful as the +3 though. Have we lost all information about field strength? We had earlier with these arrows, we had the length of the arrow, the magnitude of the field was represented. Yeah, you have lost that, but there is still some information on field strength. If the lines are closer together, if the density of the lines is high, the electric field is stronger than when the density becomes low. So if you look, for instance, here, look how many lines there are per few millimeters. And when you go further out, these lines spread out. That tells you the E field is going down, the strength.
Right, but the way he drew this, if you look at the two charges, they're completely disproportional, because he used exactly the same lines to illustrate a 1 charge as a 3 charge, and those charges will weaken at very different rates.
Of the E field is going down. It's the 1/r square field, of course. If you want to make these drawings, what you could do to make them look good, you can make 3 times more field lines going out from the plus in this case.
Okay, so he just said it. So yes, make more lines to be proportional, and then you'll understand how weak things are relative. See, in this drawing you can see that these lines here have a if you can see the mouse, have a great separation that's almost equal to the strength out here, but that's actually inaccurate, because the strength out here is there should be 3 more lines in here, so to speak. So these should be 3 times closer together than they're illustrated as being. So the force here is much stronger than the force here.
Then return to the -1. So the field lines are very powerful, and we will often think in terms of electric fields and the line configurations, and you will have several homework problems that deal with electric fields and with the electric field lines.
I don't know exactly how to fix the dilemma of this electric field, besides saying maybe they should use the word charge fields, and then at least you could understand that charge has an awful lot to do with magnetism, and you know, but maybe that's still not going to get you to the real truth of it, which is fundamentally they're different things. Electricity is a whole atom function where the electrons have pressure. It's a truth that you can use like electricity across a vacuum and create a plasma, but that's going to be made out of atoms essentially from the cathode. And the same is true for like an electron gun. It's called electricity, but you sort of see it doesn't really look like electricity. you know, and it's just, but it's the same idea of you're pushing electrons. So it's always about the electrons being pushed. That is about electricity. Electricity is about the pressure pushing an electron. And this field is about magnetism. It's about the fact that there's a charge difference. That you have to really think about it in terms of there's two forces and there's two kinds of matter bits, and you have to really understand that they're changing. Well, I mean, look, they're changing, they're converting gravity into a segregated force. It's just that, you know, once you get it, you'll get it.
If an electric field line is straight, so I have electric fields, get some red chalk. Say we have fields that are like this, straight E field lines, and I release a charge there, for instance a positive charge, then the positive charge would experience a force exactly in the same direction as the field line, because the tangential now is in the direction of the field line. It would become accelerated in this direction and would always stay on the field line. If I release it with 0 speed, start to accelerate and it would stay on the field lines. In a similar way, if we think
the catch is that matter bits, like if you have a charged substance that has mass, it'll gain momentum in that direction, and now the field will have less impact on it as it starts gaining more and more velocity. So its velocity will now be part of the equation about how much the effect of the field lines. So far he's just been using static charges, charges that aren't moving. But once you start moving charges, well, then you have a whole new thing you have to calculate into how much the field is going to affect something. Obviously, gravity, orbits, velocity is, you know, important.
The Earth as having a gravitational field. With 801, we may never have used that word, gravitational field. But in physics, we think of gravity also being a field.
Yes, well, see, that's sort of a giveaway, right? So they're just basically acknowledging that, yeah, we don't really think about bent space. We think about pressure. And that just goes back to Susskind lectures that, you know, turning into water pressure, essentially. That's how they really think about it. They don't think about it as whatever, sucking atoms and such.
If I have here a piece of chalk, the field lines, the gravitational field lines, here 26100, nicely parallel and straight.
Well, let's understand, they're also going this way, but there's just an equal number of them going this way. So the field lines are moving in this direction because he has an uneven charge. He has a +1 up here and has a -1 down here, and they're moving towards this imbalance. They're moving to a difference in pressure.
And if I release this piece of chalk at 0 speed, it will begin to move in the direction of the field lines, and it will stay on the field lines. So now you can ask yourself the question, if I release a charge, would it always follow the field lines? And the answer is no. Only in this very special case. But suppose now that the field...
So they would if they didn't gain velocity. So if the charge could move without having any momentum, that is if it was massless or something, then it would. but it's not going to if it has any mass, because now its mass has momentum in a direction, and that direction is going to potentially dominate what it does.
Lines are curved. So here are field lines, as we have seen in those configurations. It's very common. If now I release a charge in here, say I have a point charge here, it will experience a force in this direction. So it will.
So like I said, I just don't really like the way he draws this. I mean, I would draw the arrow right on the line, pointing out that at this exact location, this is the way it's moving. So I would release those lines for illustrative purposes. I would turn them into little line vectors just to get the idea that at any one point it's moving at a vector. Every point has a vector, and that line he's drawing is just a representation of the vector at that point. That's which way it's moving. At that exact location, it moves this way. It doesn't move a curve. It moves this way.
Got an acceleration in this direction, so it will immediately abandon that field line. And so if now you ask me what is the trajectory of that charge, well, it could become very complicated. I really don't know. Maybe it's going like this, and by the time it reaches this point...
So he should say maybe, based on how much mass it is and how strong the field is, will decide how much momentum it has and how far it'll go in one direction.
But I do know that then the force will be tangential to this field line, so will be in this direction. And so as it marches out and picks up speed, locally it will experience forces.
Right, so it'll experience forces which really is just rocks hitting it. So I can go 10 miles an hour and the rocks are hitting me from the side, it'll bend me. If I'm going 50 miles an hour and the same number of rocks are hitting me, it'll bend me a lot less. So, just simple gravity stuff.
Representative of those field lines, and so the trajectory can be rather complicated. So field lines are not trajectories, and not even when you release a charge with zero speed. Only in case that the field lines are straight lines. Let's now look at a field configuration which Maxwell himself, the great maestro, in some of his publications, put there. There's a ratio 1:4. And whether it is +4, +1, or -4, -1 is not important.
Well, I like that at least Maxwell didn't bother doing the arrow thing, because the arrow thing is it's deceptive. You know.
Because that's just a matter of the direction of the arrows. But Maxwell didn't put arrows in. So I leave it up to you. If it's +4 and +1, you have to put arrows going outwards. And what you see now here is this air blower effect. Think of them as both being positive. So there is the +4 trying to...
So he's just drawing two of the same charge, whether they're both plus or whether they're both minus. They're both of the same charge, and one's a 4 and one's a 1, and he's just describing the effect of their repulsion. This is how their repulsion, if you put a bunch of confetti, and they're moving into each other, you'd see, you know, this is how the see, there's no real field, so I don't really want to get into this field thing, but it's how much one thing is affecting it versus another thing in all these different locations. So you're just moving stuff around between the Earth and the Sun, and at different locations the Earth is stronger, at different locations the Sun is stronger. That's all you're doing, and you're just placing a value on those locations of, you know, 2.7. You know, how much force is hitting it.
Blow air out like a hairdryer, and the +1 is trying to do its own thing, and so you get a field configuration, field lines, which are sort of, not perhaps easy, but you can sort of imagine.
See, the deception in this is that it implies that the field lines, that the force is interacting with the force, and that's not what's happening. The force from 1 is hitting the force from 2 and causing the reflections I was talking about, and the force from 4 is hitting the 1 and causing the reflections, and so it's creating this repulsion. The forces are never interacting. The lines don't push into each other. So this is kind of a misrepresentation of the facts. It explains, you know, what is happening in terms of, yes, the pressure between the two from different locations. So if you're at one of these other locations, it's just explaining to you which one's going to dominate. So when you're horizontal to the 4, you can see that the line isn't perfectly straight this way. Yeah, you go a little bit this way, but it's not a very highly crooked line. Where if you're the small charge, the effect of the 1 will be weak and the effect of this 4 will be strong, so the line will start going crooked because the 4 is having more effect. But this doesn't have anything to do with how the two charges actually interact. The 1 is hitting the 4 and the 4 force is hitting the 1 directly.
Why it has this peculiar shape. If you put a plus test charge in between the 1 and the 4, then the 4 will repel it, but the 1 will also repel it.
So understand that he's assuming there's +4 and +1 when.
And so there's going to be a point somewhere, probably close to 1, whereby the two forces exactly cancel out. Therefore, E will be 0 there.
Right. There's the same place between us and the moon. There's the same place between the Earth and the Sun. There's always this place, like I was saying before, the neutral place.
In a similar way, between the moon and the Earth, there is a point not too far away from the moon, where the gravitational attraction from the Earth and the gravitational attraction from the moon exactly cancel each other out. That's not too dissimilar from this situation.
But let's understand, they don't really cancel each other out. The moon still pulls, the Earth still pulls. It's just doing this. There's no real canceling out. There's no light plus light equals dark. There's no canceling. There's just the fact that they're exactly the opposite amount of something. The same rock hits from both sides. You're going straight. You're still going straight.
So when you have charges of the same polarity, you always find in between somewhere a point where the electric field is 0. Let's now go to a very special case whereby I make the two charges equal in magnitude but opposite in sign, and we have a name for that. We call that a dipole.
So that's what an atom that has, like I said, the right distance between the electron and the proton to have, like right here, they're the same size. But obviously from different perspectives, you'll be able to certainly see that one's positive and one's negative. That's a better way to say it. So he's just, when he says dipole, he's saying now it's a magnet. So now he's put an electron and a proton. So that's all this example really is. Here's an electron, here's a proton. This is what they look like. It's a magnet. But as I stated, electrons and protons can be stretched, which changes it from let's continue.
Plus charge is here and the minus charge is there. Situation is extremely symmetric, as you would expect, because they have equal power. There's one air blower upstairs and one vacuum cleaner downstairs.
Alright, so again, it's just so wrong. There's nothing getting vacuumed. There's nothing moving from the North Pole to the South Pole in these weird lines. The lines just represent the force at that location. And so you use a compass needle and you'll see where the force is, how it lines up. But that line that the compass needle's making doesn't mean there's force going through the compass this way. It means it's getting hit by just as much energy on the north end as the south end in terms of it's repelling and attracting in equal proportions, and that's why the compass needle is even or parallel to the magnet, is because both forces, it's getting just as much frog tongue as it's getting rocks from at both ends inversely, and so it's even. And then if you go to some other location, it's not even. You're getting more tongues from the frog than you are getting hits from the rocks. And so those lines are not reality. They're just a representation, a way of visualizing which way proportionally, whether you're getting more rocks or you're getting more frog tongues.
If you're close to the plus charge, notice that all the field lines go away from the plus. And if you're close to the minus, notice that all the field lines come in on the minus. You expect that?
No, it's just wrong. It's just a misrepresentation of truth, and it just allows everybody to think there's some kind of magical swirling something inside of a magnet, and there isn't. Nothing's swirling around the magnet.
If you are far away from this dipole, now you have a problem.
Let's just understand, they drew those little lines, but they all know as scientists that if they put an electron there or anything, the smallest things they can put there, nothing will move on those lines. Nothing will move in the directions of those lines. It won't happen. There's no flow.
Before we had a +3 and a -1, and when you're far away, the +3 wins. So it's like having a +2 charge. If you're far away, you always expect the electric field then to be pointing away from the equivalent charge of +2. But if you add up plus and minus and they have equal magnitude, let's say +1 and -1, you get 0. So neither one wins if you're far away. And notice carefully, if you're very far away, indeed you do not see arrows either pointing out nor pointing in.
Wrong. You do. They're just neutral again. So what you can see, okay, like I said, you can't see the vibrating. The vibrating's still there. So I'm just saying, just because it doesn't look like it's vibrating, well, that doesn't mean it's not. So it's still there. There's no I blocked the force. The force, as he said before, when he originally started with the charge description, he said this stuff goes infinitely. You know, so how do you combine those two statements? There's nothing now. There's no force. No, there's still a force. It's just an equal amount, and because it's pulling you, frog tongue, rock hitting you, you're just doing this.
Nature cannot decide. There isn't one that is stronger than the other. That makes dipole fields very, very special. In the case of the +3 and the -1, if you're very far away, it's like having a +2 charge, and the E field, when you go further and further out, will fall off as 1/r². With a dipole, your intuition sort of tells you that it will probably fall off faster than 1/r². And that is part of a homework assignment that you have this week. In fact, I can already give you the answer. You have to prove it. If you're far away from an electric dipole, the electric field falls off as 1/r³.
Right, so that's interesting because, I haven't really accounted for that in some of the conversations I've had. So if they were monopoles, it's the inverse square. So it's the inverse square for, well, there's no example of a good example of a monopole besides the electron and proton, and they're not doing the inverse square bullshit. So they're not a very good example. And they're not doing it when they're in contact, obviously. At a distance, they are. But anyway, so I won't bother with an example, but it's the example I brought up the other day. You can understand when the monopoles, if I have a plus and a minus charge, there's no secondary charge producing a repulsive thing. So when a dipole, you have the you have the north side of the magnet and the south side. And the south side is always trying to do the opposite of what the north side is doing. So you can understand, well, you might be close to the north end, but the south end is still hitting you. So it's undoing, it's frog-tonguing against your rock throwing. So you're throwing rocks this way, right? So if you have monopoles, it's all rocks. But if you add the south pole, well, now there is some frog, pulling. So it's reducing this effect because it's pulling some of it back. So that's why they add the 3 to the R, is because of that effect where you're always losing something by having the dipole. If you want the strongest effects of magnetism, you want to have monopoles. Again, that's why the charge on the balloon, the magnetism of the balloon, how much it moves and it seems affected from a great distance, it's because the balloon isn't having its force diluted by having a balloon attached to it that's positively charged, and here's the negative charged one. So if you create a dipole balloons, then your effect is going to be much weaker. Your ability to move them with a monopole is going to be much weaker. Now your ability to move them with another dipole will be stronger. So if you turn your pole, then you can undo that r cubed and turn it back into r squared. So if you're measuring the field with a compass, it's r squared. If you're measuring with a monopole, a dipole, and you measure it with a monopole, then it's r cubed. So there's a catch to it.
It goes faster than 1 over r squared. There is not a single point in space where the electric field is 0.
So in spite of the fact that he implied it just a minute ago, he's having to recognize, hey, you can't get away from all these residual bits or hitting things. So it's just like there's no place in the universe that's dark. You can't go somewhere where there isn't sunlight hitting you from somewhere, so to speak.
Think about that, why that is the case. So these field configurations can be rather complicated and can be very interesting, and each one has its own applications. Are dipoles rare in physics? Not at all. In fact, they are extremely common. You cannot avoid them. Remember last time I told you, if you have a spherical atom or you have a spherical molecule and you bring that close to a charge.
So exactly the point. The atoms are essentially dipoles in the sense that they're I mean, you're never going to pull the protons out of the center of the atom. But you are going to create a distortion in the atom, and any distortion turns it into a dipole because there's more electrons on one side and less on the other side, which means the exposure to the proton is greater. So one side becomes the red end of the magnet, one side becomes the black end, the north and south side. So they dipole fairly easy by having any distortion in their geometry. Like I say, they're always a dipole. You can't turn them into a monopole. Well, see, the point is, we're back to this argument, equal size thing, and that's sort of turning them into monopoles. So if the atom is very compressed, that is, the electrons are very close to the proton, from a distance it's decidedly a monopole of proton charge. So you don't have to necessarily distort the atom in shape, you just have to change from a distance. As seen from a distance, you just have to change the pressure. Smaller electrons closer, now it becomes proton heavy. Electrons further out, now it's electron heavy. But it has to be from the right distance.
Let's now think of it, you bring it in an electric field. It's another way of saying the same thing. So we have a nice spherical atom or a nice spherical molecule, and we bring it in an electric field. The electron wants to go upstream the electric field vectors. They go against the direction of the electric field. And the positive charge wants to go in the direction.
So again, we all do it, but this isn't really good language, this wanting to. It has to be forced to. Nothing moves without it being forced to. Electrons are forced to move. Protons are forced to move. A force hits them, pushes them, moves them. So it's no want thing. You have to account that there's a force differential created by the environment that they're in. And it's that force change that causes the change in the shape.
Go downstream. And so what are you going to do? The electrons will spend a little bit more time on one side of the nucleus than they would in the absence of that electric field. And
so I would argue this is conventional physics thinks the electrons are spinning around in all kinds of ways. I would argue that no, they're locked in magnetic positions and they're jittering in those tension. And all you're really doing is changing them a minor little bit, little tiny movements in that, and that creates a difference in their charge.
Therefore, you are, through induction, turning that atom, turning that molecule in becoming a dipole. If you have a little bit more charge on this side, averaged over time, you have the same amount of extra charge plus on that side, averaged over time. So you make dipoles very often, whether you like it or not. And later in this course, we will learn more about the polarization of atoms and molecules creating dipoles when we talk about dielectrics. And you will see that it will have can have an enormous impact on the properties of the material. Could I make you a dipole here in class? Oh yeah, that's very easy. To make one of non-conductors is not so easy in class. To make one of conductors is very easy. And I'm going to do that with these two spheres that you have. Look at these two metal spheres. Conductors, free electrons, it's very easy for them to move. And I'm going to bring this rubber rod, which I will rub and becomes, I think, negatively charged, if I remember correctly, and I will bring that, say, close to these two, which are touching each other. So here is this one metal sphere, and here's the other metal sphere, and here comes the rubber, negatively charged. Ah, what's going to happen? The electrons want to go away, so this becomes negatively charged, and therefore this remains a little bit positively charged. For every one electron that is excess here, when I start it's neutral, there will be a positive excess there because charge is conserved. You can't create charge out of nothing. And now what I do, while this rubber is still here, while that rubber rod is there, I separate them. So here they're in contact with each other first. They have to be in contact. Wow, we get some visitors.
Don't be late. That means you, pretty boy.
I'm impressed. Thank you.
Cartoon behavior at college. I'd like scream something. I want my money back. I'm paying for this.
So what I do now is, while this rubber rod is still in place, I take them apart. And when I take them apart, this negative charge is trapped and this positive charge is trapped. And so I have thereby created negative charge on this one, positive on this one, and it's equal in magnitude, so I have a dipole. What I want to demonstrate...
All kind of reasonable. Let's see if I could add anything to say how this is not correct. It's, clearly the effect is going to be the strongest from where he approaches it. So if he approaches from the other side, same thing. Now if he approaches from the middle of the two balls and then tries this experiment, well, they'll probably end up with two that are the same charge. So but yes, logically this is fine.
To you is that indeed I have positive charge here, negative here. That there is a difference in polarity between these two, and that's the way that I will do the experiment.
All the atoms are now magnetizing. So when he brings the rod in, they're all magnetizing. That is, all the atoms are starting to line up, becoming little magnets. So positive and positive and positive and positive, all the way to the other side. And when he separates them, the catch here is that when he separates them, they're not going to turn into two separate magnets. He's going to separate them and create two monopoles. So he's going to create one that has more positive charge and one that has more negative charge. So, yeah, I'll have to think about that one. But that's probably just because of the distance difference. So one of the balls is going to be much closer, so it's going to have more charge on it. The other one's going to have less pressure on it. And that's really going to be the difference. And so they're both going to be dipolish, okay? But one's going to be dominated by much more positive than the other one. The other one's going to have much more negative, just because of the distance. All right, there's probably another way to say that. That'll be better. So maybe the next video I'll rephrase that.
I will not show you that the amount of charge is exactly the same on each, which of course it has to be. So let me give you some better light, or we have to get the view graph off the overhead. You see there for the first time an electroscope. We discussed it last time. It is a piece of aluminum foil, very thin, with a metal rod next to it. And when I put charge on the rod, it will also go into the aluminum foil, and they will repel each other, and so the aluminum tinsel will go to the right. And the more charge there is on it, the farther it goes to the right. So let me first put these two together, make sure they are completely discharged. And now I'm going to bring these two into an electric field, which is produced by this rubber rod. I have to rub with the cat fur, and I believe it was negative. But if you never have to remember whether it's negative or positive, of course, that is not so important. What is in a name, after all?
Well, it's a little bit, it'd be good for just clarity to understand why certain materials end up pressurizing are being the ones that get depressurized. It wouldn't hurt to know that.
But this happens to be negative. Okay, so now we go here. I bring it here. I hope that no sparks will fly over because that ruins the demonstration. And now, notice what I do. While the rod is here, I separate them. So as I was holding it there, things were going on in there that you and I couldn't see, but the electrons, the rubber rod is negative, the electrons were shifting in this direction, and this is now positive and that is now negative. If I take this one, and I touch it with the electroscope,
You sort of said that the wrong way, because the whole positive and negative thing again. The positive is the one with less electrons. Well, that's what he said. Yeah, it's moving the other way.
clearly see that there is charge on this. How can I show you now that there is charge of different polarity on the other one?
Just move it close.
Well, the way I will do that is I will approach this electroscope by bringing this sphere very close to it. And if this charge is different than the charge that is on it, the electroscope will, the reading will become smaller. And why is that? Why will the reading become smaller? Well, here is a situation of...
Probably save this for the next time. Yeah, don't need to do the whole video in one shot, right? And such. So, till the next time and such. Yeah, there we are. Thank you very much.